Hi, let's further discuss about the membrane expression process. Now we would like to look at the spiral membrane. What is the spiral membrane? Spiral membrane is a type of membrane technology that have been used in the treatment of water, especially, and also it used in industry. The spiral model is a variation of basic plate and frame concept where we are layering a few membrane. The configuration of this variable nodule is formed by a membrane envelope of spaces and a membrane wound around a porous tube like this. And when the feed mixture pressurized in the module and forced to pass through the membrane surface, selectively permeates the membrane. So for example, here is the membrane. So we will give the water here. This is our feed water, and what it do that the membrane that the what what it will do is the membrane will trap the particle and will permeate with the water, and then we will collect the water later. The feed is sent in the other direction through the feed channel across the membrane surface, and then the permeate is collected in the central porous tube. So we will have a lot of a commercial spiral module that we have a vary in size and length. So so there's a lot of it. So if we can see how it works is, for example, here is our spiral membrane, and then we give our feed solution here, and the water will pass through and will collect this capillary, this tube. So here is one of the example of the video that I can show you. Uh, so this is how it works. So here is the layer of membrane that we have, and then here is the water that we put into the membrane. So it will flow all around the membrane and will be collected in this tube, and because it's the permeate or the solution of our water, and then we go through to the tank. So we will collect it later and do another process. And then here is the retented particle. So it will go to another tank that we will treat later. So this how this parallel membrane works, and here is an actual or industrial process where we have a lot of spiral membrane here, where we have do a lot of process here. So here it looks like in industrial scale. And if we when we talk about the membrane, we will talk about folding issue. Folding issue is one problem in membrane technology, because it will generally affect the flow rate of our solution. The membrane are too expensive to be replaced for reason of fouling. So if we look at our membrane, our membrane, and the on top of our membrane, it consists of a pore. We have a lot of pore in our membrane, and if for a long process, um, the light particle will deposit to our membrane, and it makes the flow rate, where the rate or the efficiency of water to permeate membrane is less effective. Then, thus, this is we call it as a fouling issue. This long-term loss in throat-pore capacity is due mainly to the formation of a boundary layer or the accumulation of solid particles that builds up naturally on the membrane surface during the filtration process. So, so, so it makes the the separation process is less effective if we have this boundary layer which accumulate of solid and particulate. In addition to cutting down on the flood performance of the membrane, this this layer or the act as secondary membrane will remove this one. So this ability to handle the build-up of solid has also limited the use of membrane to low solid feed stream. So this is one of the constraints that we have in membrane technology, where the it we can be easily have a boundary layer, which is the accumulation of a solid and particle. If you see what is the fouling, so if you look at the fouling, so this here is the example of our membrane. So membrane. We will where we will permeate this water here, and for untreated water, we have a lot of particularly we have parasite in organic water, bacteria, salt, biopolymer, and a lot of things. So in the filtration, we permeate the water and we leave everything else, or we collect everything else there. So here is our product. So what happened here? Here, all the particle will accumulate on top of the membrane, and then it will block the pore. For example, like it will block the pore, and once it block the pore, so it make our filtration for the dye process will be less effective. So here is another illustration that I can give you. So this concentration, this content are three particle, which HPE1, H2O, and arsenic. So it only permeate uh, the water, but in the pore of at the membrane pore, it will block all of these things. So HPE1 and arsenic will block uh, the pore of the membrane, and it depends on the degree or how it block. So if it is not serious, still we can recover the membrane. But if it's serious, it will take more time to remove all the particle. For example, here if we can see membrane, so here is a example of Here is example. Here's the example of the illustration of how the folding occur. So for example, here is we have this is like our membrane that is pore. So here is standard blocking. So still we can remove it. So we can still use the membrane. And here we got is a complete blocking. So we block the membrane. So and this one is we can call this intermediate. Is how it's like how it looks like. Here is the cap filtration. This is what we doesn't want. So if we look at the flow rate, so if if we have this stage is we have still have a good flow rate. However, when you go to a complete blocking, caking, the flow rate is decreased significantly. So actually, for a good flow rate, we would like to have it look like this. Yeah. So the flow rate is gradually decreased, but this one is drastically decreased. So we doesn't have a flow rate to be like this. So we, in membrane separation process, we would like to avoid this from happening. So for if what happen if we have a what happen if we do have a membrane folding? So what we do is we block a membrane pore, so it will make the permeable flux decrease. We doesn't want it to be happen, and the efficiency will be decreased, and also the pressure time will be increased. So this is the thing that we doesn't want it to be happen, because our if we look at in the industrial perspective or in it will we need to spend more time, we need to spend a lot of time to get the same result. And of course there is a lot of cost that involve, right? So thus it make the efficiency or the production efficiency will be longer. So we need to have the same result, but we need to wait a longer time. So this is what we want to avoid. So for example here, you can compare this one. This one is a clean arrow membrane. This one is dirty arrow membrane. Where for the thin arrow membrane, there is a lot of particle that is blocked the membrane to make it less efficiency compared to the clean arrow membrane.